A tuning fork, including one made of aluminum, operates primarily based on the principles of mechanical vibrations and resonance. The two tines of the tuning fork are designed such that when they are struck, they vibrate back and forth at a specific frequency. This frequency depends on the length, thickness, and material of the tines, and any weights added to the tines can modify this frequency. The type of vibration in the tines of a tuning fork is known as transverse vibration, or flexural vibration. In this type of vibration, the motion of the particles in the medium, in this case the tines of the tuning fork, is perpendicular to the direction of the wave propagation. When you strike a tuning fork, each tine moves back and forth in a cycle. The tines move outward and inward, creating compressions and rarefactions in the surrounding air. This back-and-forth motion of the tines happens at a specific frequency, creating a sound wave at the same frequency. When weights are added to the ends of the tines, they modify the distribution of mass along the tines and can change their natural frequency of vibration. Generally, the weights decrease the frequency, resulting in a lower pitch. This is because the added weight increases the moment of inertia of the tines, which slows down their oscillation. The sound you hear from a tuning fork is actually the result of the interaction between the mechanical vibrations of the tines and the surrounding air. The back-and-forth motion of the tines creates pressure variations in the air, which travel outward as sound waves. When these sound waves reach your ear, they cause your eardrum to vibrate at the same frequency, which your brain interprets as a tone of a specific pitch. The yoke of the tuning fork is the bridge between the tines and the stem, handle, and it serves an important function in the vibrational dynamics of the tuning fork. When the tines of the tuning fork are struck and begin their flexural, transverse vibrations, these vibrations are indeed fed into the stem via the yoke. The stem in turn begins to vibrate in what is known as longitudinal vibrations. In these vibrations, the particles of the stem move back and forth along the length of the stem. These longitudinal vibrations in the stem don't produce sound directly because they compress and rarefy the air parallel to the direction of sound propagation. These parallel disturbances in the air do not efficiently produce sound waves, which require transverse motion, as the air particles just move back and forth without really transmitting energy to neighboring particles. However, the longitudinal vibrations do serve to carry the vibrational energy away from the tines, which can help to sustain the tine vibration by preventing too much energy from being dissipated as heat at the base of the tines. When considering the yoke, we can think of it as a mechanical impedance matcher. The flexural vibrations of the tines are most effective at producing sound in the surrounding air, but the air provides very little mechanical loading to the tines. The longitudinal vibrations in the stem, and any solid object in contact with the stem, provide a much greater mechanical load, which helps to pull energy out of the tines at the right rate to maintain their vibration. So, while the stem and the longitudinal vibrations it supports don't directly produce much sound, they play a key role in the overall performance of the tuning fork by helping to sustain the flexural vibrations of the tines that actually produce the sound. Standard stem length for an aluminum alloy-weighted tuning fork is about 2 inches. Based on the dimensions of this aluminum rod, we can determine the exact frequency of mechanical vibration at the base of the stem. The frequency of the sound produced by an excited tuning fork stem depends on several factors, including the length of the stem, its material properties, such as the speed of sound through the material, and the mode of vibration, whether the stem is being vibrated at its fundamental frequency or one of its harmonics. If one end of the stem is struck or otherwise excited in such a way that it vibrates longitudinally, back and forth along the length of the stem, the frequency of the fundamental mode of vibration can be calculated using the following formula: F equals V divided by 2L, where F is the frequency, V is the speed of sound through the material, L is the length of the rod. For aluminum, the speed of sound is approximately 5,100 meters per second. If the stem is 2 inches long, or about 0.0508 meters, we can substitute these values into the equation to get approximately 50,000 hertz, well within the ultrasonic frequency range required for the physiological phenomenon known as the cavitation effect in human tissue. Based on the same equation, an extended stem of 4 inches would reduce the overall frequency at the base of the stem to approximately 25,000 Hz. However, this is a simplified model, and the actual frequency can be different depending on how the stem is being excited, any boundary conditions at the ends of the stem like an attachment or extensions. The mode of vibration may also be different, for example, torsional or bending modes, which would have different frequencies. In other words, the frequency at the base of the stem can be modified when the tuning fork is gripped on the stem. Depending on the location of the grip, the overall frequency will be reduced significantly below the expected frequency of a standard 2-inch stem length. A grip at the yoke of the tuning fork will prevent any interference in reducing the stem output frequency. Finally, we should also consider that tuning forks of varying frequencies based on their weighted tine length will still produce the same frequency output at the base of the stem if the forks are a standard 2 inches. The only variance between forks of difference frequencies would be the total length and strength of flexural vibration from the tines feeding into the yoke and stem. An optimal weighted tuning fork frequency is 128 Hz, since the tine length and weight location are sufficient to provide a vibrational length and strength suitable for vibration therapy. Tuning forks of higher frequencies have shorter tines with a lower flexing capability, and tuning forks with a lower frequency have longer tines with less torsion properties and lower strength. Even though the frequency of the tuning forks are not as important in determining the overall frequency output of a weighted tuning fork at the stem, the length of the tines play an important role in the efficiency of the feeder vibration through the yoke and into the stem. Ultimately, the true therapeutic nature of a weighted tuning fork resides in the ultrasonic frequency produced by the stem, which is transferred through the base and into human tissue. From there, the mechanical vibration produces a cavitation effect, where small bubbles in the tissue fluid are created near the membranes responsible for pressurizing the interstitial fluid. The cavitation bubbles collapse at the membrane walls and temporarily change the permeability or porosity of the membrane to allow more fluid to move across the membrane and release the pressure responsible for pain, immobility, and tissue or organ dysfunction.